The Sun was formed 4.5 billion years ago and lies 149,712,000 kilometers from the Earth. Its structure consists of four main layers: the core, the radiation zone, the convection zone, and the atmosphere. The atmosphere is thousands of kilometers thick and includes the photosphere, chromosphere, transition region, and the corona. The core of the Sun is the source of all its energy. Protons and electrons within the core make up the plasma. The core can reach up to 22.5 million degrees Fahrenheit. Because of this, the high density of protons and electrons within the core move around quickly and collide with one another. These collisions cause nuclear reactions, which is the source of energy within the Sun. This energy is transported by photons to the outer layer, such as the radiation zone.
The radiation zone makes up 85% of the Sun's radius. Above the radiation zone and just below the Sun's surface is the convection zone. The convection zone is nicknamed the boiling zone because of the rolling motion of the material within the Sun, similar to a pot of boiling water.
The transition region is a very thin and irregular layer of the Sun's atmosphere. Heat flows down from the corona to the chromosphere, and in process produced into this thin region where the temperature changes rapidly. The corona is the outermost layer of the Sun's atmosphere. It is visible during the total solar eclipse as a pale white crown surrounding the Sun. The corona displays a variety of features, including streamers, plumes, and lobes. These features change from eclipse to eclipse.
The photosphere is the visible surface of the Sun, about 100 kilometers thick and composed of gas. When we look at the limb or edge of the solar disk, we see light that has taken a slanting path through this layer, and we only see through the upper, cooler, and dimmer regions. Features such as sunspots, bright faculae, and granules can be observed in the photosphere with a simple telescope. The chromosphere is an irregular layer above the photosphere where the temperature ranges from 6,000 degrees Celsius to about 20,000 degrees Celsius. At these higher temperatures, hydrogen emits light that gives off a reddish color. Solar flares, prominence and filament eruptions, and the flow of material in post-flare loops can all be observed on the chromosphere.
Solar flares, prominences, and coronal mass ejections are all a result of the solar dynamo, a magnetic generator that turns the kinetic flowing energy of charged particles in the Sun into a powerful magnetic field. These occurrences happen near areas of large magnetic activity, like near sunspots. The most benign of these extraordinary phenomena are large gaseous loops which extend out from the Sun's surface, often over thousands of kilometers. They form in about a day and can last for weeks or months, providing astronomers with an incredible view. When prominences are viewed against the backdrop of the Sun, they appear darker because their plasma is typically 100 times cooler than coronal plasma. This is known as a filament. Sometimes prominences break apart and give rise to coronal mass ejections. Coronal mass ejections, or CMEs for short, occur when large amounts of gas are ejected off the surface of the Sun. The charged particles from CMEs reach speeds of around 450 to 2,000 kilometers per second, taking about 1 to 3 days to reach the Earth, if they go in that direction. There's usually a CME at least once every 5 days, and there can be as many as 3 CMEs in a single day. The charged particles interact with the Earth's magnetic poles, creating aurora. Flares occur when the Sun releases a massive amount of electromagnetic energy. They go through 3 stages in their lifespan. The precursor is the initial release of energy. The impulsive is when ejected protons and electrons are accelerated, emitting large amounts of radio waves, gamma rays, and X-rays. The final stage, decay, is the buildup of X-rays and their decay. The duration of each stage varies from a few seconds to a few hours. Here on Earth, solar flares are responsible for the interruption of low-frequency radio communication, which, if intense enough, cause radio blackouts, disabling all low-frequency radio transmission in the affected area. All of these occurrences can be quite extraordinary and strongly influence the solar wind. More about that in a moment.
In 1945, the world saw the capabilities of nuclear power when America dropped the first nuclear bomb on the Japanese town of Hiroshima, obliterating it within seconds. By learning to utilize the power generated by nuclear fission, the splitting of atoms, the United States obtained immense world influence. However, humans are still racing to harness the full potential of nuclear reactions. Nuclear fission, which we have harnessed, is about 1 million times more powerful than the average nuclear reaction. Nuclear fusion, which we have yet to harness, is about 3 to 4 times more powerful than nuclear fission, and therefore 3 to 4 million times more powerful than the average chemical reaction. Nuclear fusion is the opposite of nuclear fission, so instead of forcing atoms apart, you force 2 atoms together. While joining atoms together sounds simpler than splitting one, It actually requires extremely high temperatures and lots of energy. The only place capable of sustaining these conditions naturally is the core of a star. In a process called stellar nucleosynthesis, high-energy hydrogen atoms collide and combine to form larger and more massive elements. In the case of our Sun, the kinetic energy of hydrogen atoms skyrocket due to its temperature, and they collide with each other, creating deuterium and tritium and then on to helium-4. Stellar nucleosynthesis is one of the few instances in reality where matter is not conserved. Instead, a portion of the two atoms' mass is converted into photons. The resulting energy from this enormous exothermic reaction is then harnessed. Due to its size, the Sun burns about 600 million tons of hydrogen every second. At its core, the newly formed helium atoms are then pushed towards the outer layers of the Sun, while gravity presses them towards the center, preventing the Sun from disintegrating.
Vacuum of space. From pictures and movies, it looks so quiet, peaceful, and still. The reality, however, is that it's not. Space is actually filled with solar winds, storms, and all kinds of waves. The surface of the Sun is cause for much of what we know as solar weather. Sunspots in our Sun's corona, its outer layer, are caused by the intense temperature the corona can reach, up to 2 million degrees Fahrenheit. At this level of heat, the Sun's gravity is unable to hold onto the fast-moving particles, causing them to be released into space. These streams that are emitted are known as coronal mass ejections, or solar wind.
Material carried by the solar wind can sometimes reach a planet's surface. This does severe damage to any life that might exist on it. Earth has a magnetic field which serves as a shield, thus redirecting the material around the planet so that it streams around the Earth. The force of the wind stretches out the magnetic field so that it is smushed inward on the sun side and stretched out on the night side.
Solar wind and coronal mass ejections aren't the only components of solar weather that affect us here on Earth. The most important and well-known impact of space weather to the Earth is the brightness of the Sun. The Sun emits photons of light that carry energy to the Earth at a constant rate. We call the energy gained from these waves the total solar irradiance. The TSI has been measured to be 1,365.6 watts per meter squared at minimum and 1,366.5 watts per meter squared at maximum. Even this small difference of less than 1 watt per meter squared can cause a noticeable change in our temperature. Cosmic rays are another part of space weather. Cosmic rays are high-energy charged particles traveling at nearly the speed of light that strike the Earth from all directions. Most cosmic particles are nuclei of elements throughout the periodic table. When high-energy cosmic rays collide with the atmosphere, they create a shower of secondary particles that don't cause much radiation to people here at sea level. However, these rays at high altitudes and in space are a hazard to astronauts and can cause
People travel from all around the world to see them. They are probably one of the most studied astronomical events ever. For a long time, and by many civilizations, they have been thought of as magic. But now, we are able to understand the reason why this phenomenon occurs. The word aurora comes from Latin, meaning dawn of the north. They actually happen in both the north and south poles, but due to the lack of land to observe from in the south, the most popular ones are those from the north. They are distinguished by the names Borealis and Australis. We must first know that the Earth's molten iron core has such immense gravitational pressure that it creates a magnetic field around it, called the magnetosphere. When positively charged particles from the Sun travel at such high speeds, with a very high energy charge, some push through the magnetosphere at the northern and southern poles. This is because the magnetic field is the weakest at the poles, so the particles can get through here rather than bounce off. Once these particles encounter oxygen and nitrogen, they transfer energy, which is then released as photons. The altitude in which they collide, as well as how much oxygen and nitrogen there is, alters the colors. For example, oxygen at lower altitudes produces green, whereas at higher altitudes it produces a reddish color. Nitrogen generally produces blue, Often, these colors occur at the same time during the auroras, making the show even more spectacular. Borealis happens almost every winter night, between September to April, but can only be seen on clear nights, which are rare during these times. These are usually viewed in the winter because the night sky has to be fairly dark. This makes it hard to see because it is so unpredictable, for it is dependent on the weather. Therefore, it's hard to plan a visit to witness this fantastic spectacle.